Welcome back to the podcast, where we explore the intriguing world of technology and systems design. Today, we're diving into a topic that impacts all of us who rely on computer networks: network reliability. Despite all the advancements we've made over the years, network issues are still surprisingly common. So, what does this mean for our systems, and how can we better brace ourselves for those inevitable hiccups? Let's unpack this together. To start, when we think about network reliability, we often picture things like error-correcting codes and protocols such as TCP, which are designed to ensure data travels from point A to point B without any loss. But even with these technologies, there are limits. For example, while error-correcting codes can manage a few single-bit errors, they struggle when interference overwhelms the signal. Similarly, TCP can mask problems like packet loss and duplication, but it can't eliminate delays caused by the network itself. This tells us that even with sophisticated systems in place, challenges remain in ensuring reliable communication. You might be asking yourself why, with all the technological advancements, network issues still persist. The reality is that faults can occur even within the most controlled environments, such as a company-operated data center. Research indicates that a medium-sized data center can experience around 12 network faults each month. Interestingly, half of these faults might disconnect a single machine, while the other half could take down an entire rack. Adding redundancy, like extra networking gear, doesn't always solve the problem, especially when human error, like misconfigured switches, comes into play. Public cloud services, like Amazon EC2, are particularly notorious for transient network glitches. Even well-managed private data center networks can face instability. For instance, a software upgrade on a switch might inadvertently trigger a reconfiguration of the network topology, leading to delays that last over a minute. And we can't overlook the unexpected scenarios, like sharks damaging undersea cables or a network interface dropping inbound packets while still sending outbound ones. Just because a connection works in one direction doesn't guarantee it works the other way. When a network fault happens, it can lead to what we call a network partition or net split. For clarity in our discussion, we'll refer to these issues as network faults to avoid confusion with storage system partitions. The essential takeaway here is that network communication is inherently unreliable, and our software must be designed to handle these faults gracefully. Now let's consider the implications of these network issues. If a fault occurs, your system might enter a state where it can't serve requests, potentially leading to deadlocks or even data loss. This is why it's so important to understand how your software reacts to network problems and to ensure it can recover from them. Some organizations even adopt practices like Chaos Monkey, which deliberately triggers network faults to test system resilience. A critical aspect of managing network reliability is detecting faulty nodes. For example, a load balancer needs to stop sending requests to a node that has gone down, and in a distributed database, a follower must be promoted to leader if the current leader fails. However, detecting these issues isn't always straightforward. Sometimes you might get feedback indicating a problem, like a TCP connection being refused because the process has crashed. But if a node crashes while handling a request, you might not know how much data was processed. In many cases, detecting faults relies on timeouts. But how long should these timeouts be? A long timeout can lead to delays for users, while a short one risks declaring a node dead when it's just experiencing a temporary slowdown. This balancing act is crucial. If a node is prematurely declared dead, it can place additional load on other nodes, worsening the overall situation. Imagine a scenario where multiple nodes are trying to communicate at the same time. If the network switch gets congested, packets may need to queue up, leading to delays. If the queue fills up, packets can be dropped, requiring retransmission. This is where TCP's flow control comes into play. but it doesn't eliminate the delays experienced by the application. The application sees the result, a longer wait time, without being aware of the underlying packet loss and retransmission. To illustrate this, think about how travel times on a road network can vary due to congestion. Similarly, packet delays on a computer network often stem from queuing. If multiple nodes send packets to the same destination, the switch has to manage the flow, which can lead to delays when the network is busy. Once the packets reach their destination, if the CPU is occupied, the operating system will queue incoming requests until they can be processed. In virtualized environments, this queuing can get even trickier, as virtual machines may pause, further increasing delays. So, what can we do to navigate these challenges? First, we need to accept that network faults are a reality in distributed systems. Our systems should be designed with resilience in mind, capable of handling failures gracefully. This means implementing robust error handling, automatic fault detection, and recovery mechanisms. Additionally, testing systems under fault conditions can provide valuable insights into their reliability. By simulating network issues, we can observe how our systems respond and make necessary adjustments to improve their resilience. In conclusion, while we've made significant progress in building reliable networks, the truth remains that faults are still common, and we must prepare for them. By understanding the limitations of our technologies and designing our systems with resilience in mind, we can better navigate the challenges of network reliability. Thanks for tuning in today. We hope this discussion has shed some light on the complexities of network reliability and inspired you to think critically about how you design and manage your systems. Join us next time as we explore more fascinating topics in the tech world. Until then, stay connected.